So maybe let me share.
Yeah, go ahead.
Let me share my screen. Okay, can you see the full screen?
Yeah, that's good. Okay, well, let's go. It's good to see all of you here. This is the second of our series of seminars, joint seminars by prospective postdocs. So today we're going to have another two speakers, more in the realm of astroparticle cosmology, that sort of thing. So our first speaker is Yen-Hsun Lin from the Academia Sinica in Taipei. So Yen-Hsun is a postdoc there, but before he was there, before he joined there in 2019, he was a postdoc at the National Cherenkov University and a PhD student at the National Chiao-Tung University. Yen-Hsun has worked on various things related to dark matter and neutrinos and indirect detection. So thank you very much for agreeing to be part of this series, and why don't you take it away? Thanks.
Okay, thank you. Thanks for the introduction. So good afternoon, everyone. My name is Yen-Hsun. So this is a talk today I want to share with you. So basically in the following talk, I would like to tell you the story that how we use the supernova neutrino and neutron star temperature to probe dark matter from light to heavy. And this project is working with my collaborators listed here. So we just published one paper. So we hope we can finish another one by the end of this year. Okay, so I presume that maybe some of the audience are already familiar with what dark matter is, but I think I still need some pages to do this introduction stuff on the dark matter direct and indirect search. And then I will move to the motivation for this project. That's why we focus on the supernova neutrino and neutron star. Okay, so let me get started. So this is we, the Earth. So if we look into the deep space, we can find the traces of dark matter at different scale, such nearby our solar system, in the Milky Way scale, and the local group, or even the entire universe, based on these observations. So these observations suggest the existence of dark matter from its gravitational influence on the stellar object. In addition, these scales from inner to outer circle, they not just indicate the spatial dimension, they also indicate the temporal evolution from the very ancient epoch to the very present day. So basically, we can say that dark matter is not only abundant in space, but also stable against time. So we found dark matter everywhere in the universe. However, these observations, they did not tell us what dark matter really is. So suppose dark matter is a kind of particle, then it should have a mass. So it could range from very light to very heavy. So in order to pin down this question, so we have to set up some measurement by assuming there is non-zero interaction between the dark matter and stellar model particles. So these detectors, plenty of detectors are built on the Earth to measure the dark matter at different mass scale. And because these detectors, they measure the direct recoil from the scattering between dark matter and target material, so they are called dark matter direct search. So in addition to the direct search, we can also view this problem from the astrophysical environment, such as our Milky Way. So it is believed that there's a lot of dark matter gathered in the center of our Milky Way. So suppose anti-dark matter does exist in the current universe, and it can annihilate with the dark matter and produce visible signatures, such as photons or neutrinos. They can be measured by the detectors on the Earth. One advantage for Milky Way is that it actually sensitive to all kind of dark matter mass, a very, very wide range on dark matter mass, but it can only probe dark matter annihilation cross-section. So if we want to probe other types of dark matter interaction, we have to look for other targets, such as our sun. So our sun is not only sensitive to the dark matter annihilation, it also sensitive to a dark matter background interaction, dark matter self interactions. In addition, if dark matter is multi-component, we can also study the relevant kinematics in the sun. But our sun is only sensitive to a narrow mass range from GeV to TeV due to the dark matter evaporation and strong attenuation on the high energy signature. So besides the Milky Way and our sun, so our Earth is another probe for dark matter. It is sensitive to a dark matter mass heavier than 50 GeV. It also sensitive to these two types of dark matter interactions. So this is a brief introduction on the current status of dark matter, direct search, indirect search. My recent works on the Earth capital dark matter and solar capital dark matter are listed here. Okay, so now let me move to the motivation of this project, that why we target on the neutron star and supernova neutrino. So neutron star, it has a very good benefit that because it is sensitive to dark matter mass with a very wide range, large range from keV to TeV and beyond. So suppose dark matter can be captured by the neutron star and annihilate inside it, then this effect, this kind of effect generates heat and change the surface temperature of the neutron star. So future telescopes such as James Webb Space Telescope that is going to launch soon can measure or can observe the surface temperature of the nearby neutron star. Therefore, we can use such observation to constrain the dark matter properties. However, there's a serious flaw for neutron star. If dark matter mass is smaller than the chemical potential, electron chemical potential of the neutron star, roughly speaking, around 100 to 150 MeV-ish, then the annihilation channel to leptons, particularly speaking, to electrons will be Pauli block. So this means that neutron star, the capability of neutron star to probe light dark matter is in general not possible. So if we want to probe a lighter dark matter, lighter than 100 MeV, or even much lighter than keV, we have to look for alternative solution. And we found that supernova neutrino is actually a very suitable place for probing light dark matter. So these new supernova neutrinos will upscatter the dark matter in the halo. So once this dark matter, the halo dark matter is upscattered, then can be further detected by the water and Cherenkov detectors on the Earth, and can make some prediction. So this is why we look for these two targets. And by combining the two, you can clearly see from the cartoon on this page that the sensitivity to very wide dark matter mass range are down to, it can even down to electron volt and much beyond TeV. So my collaborators and I already studied a lot on the neutron star, and now we are working on the supernova neutrino case. We hope we can finish it soon. So this will be the motivation and introduction of this talk. So let me move to the first topic of this talk, that dark matter boosted by the supernova neutrinos. So, so let me use one page to briefly introduce the idea behind this topic. So suppose there's a supernova explosion at the center of our galaxies. So this is some basic information for the supernova neutrino, that when the star explodes, the duration time is around 10 seconds, and it will emit countless neutrinos, and each neutrino, generally speaking, carries average kinetic energy between the 10 to 15 MeV. So suppose these supernova neutrinos encounter dark matter in the halo, such as this supernova neutrino meets another dark matter here. So in the beginning, the dark matter is almost at rest. The halo dark matter is almost at rest with zero kinetic energy. However, after the scattering, this halo dark matter can gain kinetic energy from the supernova neutrino. And after the scattering, the moving direction of this a boosted dark matter is not necessarily the same as the incoming direction of the supernova neutrino. It could be deflected by a scattering angle alpha. So the angular distribution for this alpha can be precisely determined by the relativistic kinematics. So here I want to use this figure to show you the angular distribution of this alpha depends on the dark matter mass and the kinetic energy. So for this 1 keV case, after the scattering, dark matter is relativistic. So the moving direction of this relativistic dark matter, the scattering angle, the distribution of this angle alpha for this relativistic case is much narrower, which means that the dark matter will move along the direction that is very, very close to the original direction of the supernova neutrino. However, if dark matter is heavier, then as you can see from this plot, the angular distribution is much broader. So although after the scattering, the angle alpha is allowed within a certain range, but only a specific direction, only a specific alpha that points the line of sight direction can contribute to the boosted dark matter flux at the Earth. So this is a basic notion of this project and the geometry behind it. So in our calculation, we try to take all of this into account. Okay, so let me use another page to briefly describe what's the boosted dark matter flux, or so-called the BDM flux at the Earth. So this is in this plot, we assume the angular distribution can be described by a delta function. So this is so-called the single direction approximation, which is generally true for the relativistic case. If you still remember the lesser plot that for the relativistic dark matter, the angular distribution is actually very, very narrow. So in this demo plot, I will take this approximation. So this is the flux, and this is the timing information of the BDM flux. So you can see from this plot that the BDM flux is actually time dependent, and the timing starts from the arrival of the first supernova neutrino. And you can also see that the duration of the BDM flux is actually much longer than the duration of the supernova neutrino. So this is because dark matter mass is actually much, much larger than the neutrino mass. So after the scattering, even dark matter is relativistic. Its velocity is still much smaller than the speed of the light. So it takes longer time to propagate to the Earth. So that explains why the BDM flux will not arrive the Earth simultaneously with the supernova neutrino. And of course, if dark matter is lighter, then the velocity will be larger, then it will arrive Earth earlier compared to other light dark matter mass. Sorry, compared to other heavy dark matter mass. And you can see that there's a cutoff for each BDM flux. So the cutoff time indicates the dark matter came from the explosion site. So one cannot find any dark matter came from the place longer than this distance. So this cutoff time also depends on the dark matter mass uniquely. So if we know what kind of dark matter mass we want to analyze with the data, then we can use this cutoff time to determine the detector exposure time. Because even the exposure time is longer than the cutoff time, it only increases the background instead of the event rate. So by knowing this cutoff time in advance, we can use such information to minimize the background and maximize the event rate. Therefore, we can get better sensitivity results. So this is a very interesting time-dependent feature of the BDM flux. Therefore, we can use it to control the background rate. And in this last slide of this topic, I want to show you the projected sensitivity of this BDM scenario from a supernova explosion in our galaxy center. So in this analysis, we assume the sensitivity is two sigma detection significance And the detector is very similar to Super K, which has 30 kiloton mass. And of course, we use this cutoff time to determine the detector exposure time. But for some heavy dark matter, the cutoff time will be longer than 30 years, but we don't want to spend so much time waiting for this event. So we set a cutoff for this exposure time is 30 years. And this is how we calculate the event rate. So as you can see from this formula, that there are two cross-sections. One is the dark matter neutrino cross-section, which is responsible for the boosted dark matter. And the other is the dark matter electron cross-section, which is responsible for generating event inside the water Cherenkov detector, such as Super K. And because we are doing the model independent analysis for this scenario, so for simplicity reason, we assume both cross-sections are the same. And this is the sensitivity plot. So the vertical is the BDM sensitivity on dark matter neutrino cross-section, and the horizontal is the dark matter mass. And there are some color shaded regions that indicate the current existing bounds from the direct search, solar reflection, and other type of boosted dark matter from cosmic ray. So these red lines are the BDM sensitivity. So you can see that the BDM sensitivity is actually much better than the current existing bound, many order of magnitude better. And particularly speaking, if dark matter is lighter than a few MeV, then the BDM sensitivity outperforms the current direct search bound. And of course, the sensitivity can extend down to electron volt dark matter mass. So we use this plot to demonstrate that the BDM scenario is actually very good for probing light dark matter. However, if dark matter mass is heavier, particularly speaking, heavier than the average supernova neutrino, then the BTL sensitivity becomes much worse. So we have to look for other detection method to probe the high dark matter mass region here. So that would be the next topic of this talk. So in the next topic of this talk, I will try to tell you the story of the neutron star, that how we use neutron star to constrain the heavy dark matter mass region. So again, I still want to use a few pages to describe the general idea behind this framework. So here, this is a neutron star. Usually for a neutron star, it has a very strong gravity. So suppose the halo dark matter gets attracted by the neutron star's gravity and falls into the star, assuming there's non-zero interaction between the dark matter and the baron inside the star. So when I say baron, I usually mean the neutrons, because neutron is the richest element inside the neutron star. So when this dark matter falls into a star and can further scatter with neutrons or the barons inside the star, after the scattering, if the dark matter could lose significant kinetic energy and makes its final velocity smaller than the escape velocity, this dark matter will be permanently trapped by the neutron star. So this is what we call the capture rate of the neutron star. So capture rate, in principle, capture rate increases the number of dark matter N-chi inside the star. But we also assume anti-dark matter exists in the current universe. So neutron star can capture anti-dark matter as well. So both can annihilate. An annihilation process will take dark matter away from the star, which decreases the number of dark matter. So by including these two competing effects, we can write down differential equations that governs the evolution of N-chi inside the star versus time. But after a certain period of time, the strengths of these two competing effects becomes equal. So that means the whole system becomes equilibrium. So after the equilibrium, the total number of dark matter N-chi inside the star will remain a constant. Therefore, we can use this number to calculate the total annihilation rate of dark matter inside the star. So suppose the annihilation product contains the number of fermions or standard model particles, except neutrinos. So these standard model particles, they will experience a multiple scattering due to the baron density. Neutron star baron density is actually very, very high and gradually deposit kinetic energies to the star. So this effect generates heat. So this is the basic notion of dark matter heating through the annihilation. But what kind of annihilation product is actually determined by the particle model behind it. So in this topic, we assume the kinetic mixing plus Vmax mixing model that we use this model to describe the interaction between the dark sector and standard model sector. Also, this model gives us the prediction of the annihilation products. And interestingly, this model will also introduce a new dark gauge boson we call V. So the first case for the annihilation is that if this V, the new gauge boson V, is heavier than the dark matter mass, then it cannot be produced onshore. So the dark matter annihilation will directly produce a pair of standard model fermions. On the other hand, if the V gauge boson mass is lighter than the dark matter mass, then of course we also assume the dark sector coupling is much stronger than the coupling between the dark sector and the standard model sector. Then the annihilation channel will be dominated by the two gauge boson. But this new gauge boson V also couples to the standard model particles, so it can decay before it left the star. So this channel also contributes to the heating effect. So this is how annihilation generates heat. If you still remember what I just said about this capture process, in order for dark matter to be captured, it must transport a kinetic energy to the star. So this is another type of energy injection. So by including these two heating effects, if they are strong enough, then the surface temperature of the neutron star will be affected by the dark matter. So before telling you the result, let me briefly discuss the cooling mechanism, the standard cooling mechanism of neutron star. So when the neutron star was born, it actually suffers from two kinds of, it actually suffers from internal cooling due to these two emissions. One is the neutrino emission and the other is photon emission. So in the beginning, when the neutron star was very young, its temperature, of course, is very high. But when it grows older and older, the temperature becomes colder and colder. So for 5 giga-year-old neutron star, the standard cooling mechanism predicts that its temperature is could be around 100 Kelvin. But if we include the heating from dark matter, depends on what kind of dark matter properties are, the heating could raise the temperature of the neutron star up to more than 3000 Kelvin. So by measuring this temperature deviation, the future JWST telescope may have the capability to observe such kind of deviation. Then we can use such deviation to constrain the properties of dark matter. So here I want to show you the numerical results of the neutron star temperature depends on the mixing parameter between the dark sector and standard model sector, as well as the dark matter mass. So the rainbow color indicates the temperature of the neutron star. So if the color moves toward red, means that the neutron star surface temperature is higher. However, if the color moves towards purple, it means that the temperature is more likely to be the prediction from the standard cooling mechanism. So let's focus on this left plot here. So in this plot, we assume the dark matter, this is the dark matter properties, and we also assume the mediator mass, the new mediator, is much heavier than dark matter mass. So based on this plot here, we also show the direct search bounds with these cyan lines. So you can see that in this parameter space, direct search only constrains a very small fraction of the parameter space. However, neutron star can provide wider sensitivity on dark matter parameter regions. So which means that the neutron star is actually a very good complementary probe in addition to the dark matter direct search in the region that this direct search is insensitive to. So the situation is similar for the light mediator case. So the statement remains the same, But due to the mediator is lighter, then of course the kinematic will slightly change. But actually, the conclusion is similar to the heavy mediator case. Okay, so this will be all the topic I want to discuss with you today. So let me briefly conclude. So in this short presentation, we demonstrate two scenarios for probing dark matter. One is the supernova neutrino boosted dark matter, and the other is a neutron star surface temperature. So both methods cover a very wide range of dark matter mass, and they also provide a much improved sensitivity. So depends on what kind of dark matter mass we are going to analyze. If it is light dark matter, then we can turn our attention to the supernova neutrino BDM. If we want to focus on the heavy dark matter, then we can use the neutron star temperature. And we also found that the BDM contains a very interesting time-dependent feature, such as the cutoff time. So if we know the cutoff time in advance, that the cutoff time, of course, depends on dark matter mass uniquely, then we can use it to control the exposure time and get better sensitivity analysis. And of course, the two scenarios provide very rich understanding on a variety of dark matter properties, such as mass and different kinds of interactions. Okay, so this is all the stuff I want to tell you today. So I should stop here and start taking some questions. Thank you.
Great, thank you very much for that talk and for keeping so well to time. Let's have a few questions. Anyone just have a question? Just go ahead and shout out.
Yeah, I have a question. So
Sure.
I was interested in the supernova boosted dark matter scenario. So because in structure formation, there was if supernova feedback is like a significant component that you have to take into account when you talk about like the evolution of like large scale structure. Do you have like an estimate? Would this add to that? Like since the dark matter, if a supernova goes off, then it looks like that the local dark matter distribution will get kind of blown out a bit. So it's like a even more exaggerated supernova feedback in the scheme of things. Is there like a ballpark number on, do you expect some kind of suppression on the power spectrum?
I see, but I think what you mentioned, the star formation rate actually happens earlier, right? So in this scenario, we are looking for a late time universe, but we didn't estimate what you are asking, but we did estimate the total number of dark matter can be affected by the supernova neutrino, which means how much dark matter can be obfuscated within according to a one supernova explosion. So the total number of dark matter is many order of magnitude than the total neutrinos can be emitted by the one single supernova explosion. So by comparing with the total number of dark matter in the Milky Way halo, depends on what kind of profile you are using, we think that the total number of dark matter being obfuscated by the supernova neutrino is actually much smaller than the total number of dark matter in the halo. So we think, this is just a guess, we didn't do any thorough calculation, but we guess the supernova boosted dark matter will not affect the structure of the of our halo structure. Yeah.
Okay, great, thank you.
But this is actually a very good question. We will do more thorough analysis later. Yeah.
Okay, sounds good. Thanks.
Anyone else? I might ask a couple of questions just quickly before we go on to the next speaker. So can you go to the plots where you were showing the bounds for the supernova neutrino dark matter constraints? Yeah, this one.
Yeah, this one.
What is so this is a neutrino dark matter cross section. How do you do a direct search for a neutrino dark matter cross section? This green band, yeah. How does that derive?
Yeah, so here's a tricky part, that because we didn't have any model inside it, so in principle there's no way to connect the dark matter neutrino cross section and dark matter electron cross section, right? So but this is also benefit for the model independent search. So in this analysis, we simply assume that the neutrino cross-section is the same as the dark matter electron cross-section. But we are talking, my collaborators and I are talking the next step of this framework. So we will put some particle models in the analysis. Therefore, we can connect the two, the dark matter neutrino cross-section and the dark matter electron cross-section. Therefore, they can be compared together. Yeah.
So this bound is coming from things like Xenon and Sensei and experiments like that.
Yeah.
Yeah. The other thing I want to quickly ask is, do you need to worry about the like some kind of like attenuation of the signal from like solar neutrinos or stellar neutrinos as that they might collide with? Because you will have solar neutrinos going up to sort of MeV scales, perhaps. So
yeah,
then I don't know if that's a relevant effect at all, but I don't know if it's something you checked.
Yeah. So well, the DSMB, I think the main effect that you mentioned would be the DSMB, the diffuse supernova neutron background, which is universal existing in our universe. But compared to the BDM flux here, the DSMB flux is much suppressed. So we think that the DSMB will not affect this boosted dark matter flux at the Earth. On the other hand, for the solar neutrino has a preferred direction. So our detector can precisely determine where the solar neutrino comes from. So therefore, if we can somehow look for other, we can analyze our data, the BDM data that is not in the same direction as the supernova neutrino, so we can avoid this problem in the analysis. Yeah.
Okay. Yeah, makes sense. All right. Well, let's thank Yen-Hsun again, and we can leave it there and go to our next speaker.
Okay. Thank you.